Subroto and Kedar for giving me the opportunity to speak about something which I have been at for the last few years. What I am going to tell you today is our work on superconductivity in iron arsenides, basically, which takes an alternative intermediate to strong coupling view of iron arsenides. And I apologize to begin with for the fact that I'm using an older file, which is basically when I was still at Institut Lollanjava. But hopefully this will not affect the content of what I am about to talk. So what I'm going to start with is an experimental review, which wherein hopefully I'll motivate or set a stage for the kind of modeling that I'll be concentrating on, which is basically a theoretical technique tailored to systems which are close to a Mott transition, but may not be Mott insulators. And I'll use this modeling to basically show that a wide variety of observed facts can be rationalized in an intermediate to strong coupling view, and use those strengths to basically tell you about picture wherein competing orders result directly from an instability of a bad metal without Landau quasi-particles. I'll follow this with outlook and conclusion. Okay, so before I go that, in a lighter vein, there's a joke which is especially relevant to the kind of approximations used in strongly correlated quantum matter, which is basically sketched out here. Right. So, okay, so, right. So, with that, it's just an example of the crystal structure of iron arsenides. These are, in analogy with cuprates, layered materials, but less two-dimensional than the cuprates. The basic unit, which is basically active space, are the iron arsenic layers with spacers of lanthanum, oxygen, where the fluorine doping occurs. So as in the cuprates, the doping can sometimes occur in the spacer layers, not directly in the iron arsenic plane, though in the 1-2 materials, one substitutes cobalt in place of iron directly in the planes. However, that's a magnetic impurity, not a non-magnetic one. Okay, so after this first discovery of elevated temperature superconductivity in iron arsenides by Kamihara and co-workers, flurry of activity, which basically where people discovered a whole lot of systems, so-called 1-2 systems, which have a structure similar to many F-electron systems and so on. Also, single-layer FESE systems are structurally very simple, but it's important to remember that the basic physics is always in this iron arsenic layers, and that the anisotropy is much less than in the cuprates. Okay, so the first thing one worries about when one looks at a new material is basically the correlation between the structure and fermiology. And in this case, since there are 5d orbitals on iron which get split in a slightly different way compared to the perovskites by a crystal field splitting, which has S4 symmetry, but the 5d bands still cross for the Fermi energy in band structure calculations, and the resulting Fermi surface for the 1-1-1-1 iron pnictides basically sketched out here. Okay, so you can get that kind of Fermi surface by doing a standard density functional calculation. In the tetragonal structure, the XZ, YZ orbitals are degenerate, but however, they are appreciably mixed with out-of-plane Z-square states for the gamma pocket, which is the central pocket. Another novelty is basically that, like in strontium ruthenate, there is an appreciable warping of the Fermi surface along Kz, and that may have implications for the detailed structure of symmetry of the gap function in these systems, as I will come to. One thing one basically sees is that when one compares density functional calculations to Diaz von Alphen data, this is by Amalia Koldia, there is broad agreement, but there are also important differences. For example, one of these bands, which is Z-square band, does not appear in the experimental Diaz von Alphen's spectrum. And the other bands can be matched with the experimentally observed ones by shifting them by orbital dependent amounts. What is also important to notice is basically that the topology of the bands is basically very close, almost indistinguishable from what you would expect from DFT calculations. So if one were talking about many body renormalization, that has very weak momentum dependence, but as I've come to appreciable frequency dependence. Okay. So this is another example for LAFEPO, wherein you see that the Fermi surface corrugation out of plane is appreciable, and in fact, this may have something to do with the fact that the, one observes nodal superconductivity in this system, as in many of the 1 to 2 ion arsenides, which I'll come to. So for the 1 to 2 ion arsenides, basically you can see the very complicated Fermi surfaces. So in the tetragonal phase, you have this central pocket which is appreciably warped along the c-axis, and so are the whole pockets at the corners of the Brillouin zone. In the collapsed tetragonal state, this is drastically modified, as well as when one undergoes a transition from the tetragonal to the orthorhombic state, followed by antiferromagnetic ordering, which always occurs in the orthorhombic state. So one thing before I proceed is basically you see that the kind of antiferromagnetism one observes here is stripe antiferromagnetic ordering, with ferromagnetic ordering along B and antiferromagnetic along A and antiferromagnetic along B. So that occurs due to the fact that if you look at the kind of the quantum chemistry in ion arsenides, the hopping between I and D or states occurs via intervening arsenic, which lies either slightly above this plane or below this plane in a kind of staggered way. So the hopping, so the direct DD hopping is actually modulated by hybridization with the arsenic P states, and the diagonal hopping is actually of the same order as the nearest neighbor hopping on an effective square lattice. So that implies a large frustration in an effective J1, J2 picture in a strong coupling limit. One would naturally expect stripe antiferromagnetic states, and these are precisely what are observed. Okay, so up to this point, there is no compelling reason to basically question a microscopic Hamiltonian which might have arisen from density functional features. What starts creating difficulties are when you go a step deeper and look at changes in Diaz von Alphen spectra as you basically move through as you basically dope the material. So this is for the 1 to 2 phosphorus doped case. You see that superconductivity actually enhances exactly around the point where the effective mass of carriers in the beta sheet diverges. And the beta sheet is actually lost as you cross this line, as you cross optimal doping. Okay, this is basically data by Amalia Cordia again. And it rings a bell because exactly what happens in other systems as well, near quantum critical points associated with magnetic order or otherwise, and most notably in cerium, rhodium, indium 5. Additional features which basically arise can be gleaned from a study which was performed basically by Basov and co-workers in the early days of ion pnictides, where they basically looked at the degree of correlatedness, which is basically the weight of the Drude low frequency component in the optical conductivity to the band structure value evaluated from DFT. And you can see that basically the ion arsenides lie in a region which is associated with correlated metallicity. In fact, they lie close to the cuprates, to doped cuprates, in contrast to very good metals where this ratio is almost 1. Here it can be decreased to 0.2 of the band structure value. So well, that would seem to suggest that one should basically treat these as strongly correlated materials. That is actually also seen from the direct optical conductivity data as well, wherein a very small coherent component sets in subsequent to the structural distortion and in the antiferromagnetically ordered phase. But if you go above in the normal state, without any symmetry breaking, the optical conductivity is very broad, and it's difficult to discern any long-lived quasi-particles from the kind of optical conductivity that is seen. Okay? So that would suggest that iron arsenides are basically at least in the intermediate to strong correlation limit, not as strongly correlated as the cuprates maybe, which are Mott insulators. These are not, though there are recent examples which are true Mott insulators, which I will not talk about. So if you look at similarities in the phase diagram between very different materials, this is phosphorus dope 1 to 2. This is basically high temperature cuprates, and it's basically restricted to the doping range beyond optimal doping where superconductivity peaks. This is SR3RU207, which shows metamagnetic quantum criticality near as a function of field, and these are 1D organics. So what is common to all of this is near a so-called optimal doping or optimal pressure or whatever external parameter you are tuning, the resistivity is always a linear function of T. So this light blue region is where the resistivity exponent is 1. It's taken from Sachdev and Keimer physics today. So what you can immediately see is all these systems are very structurally very different. This is quasi 2D, but with small anisotropy. The cuprates have very large anisotropy. These are quasi one-dimensional materials and so on. But they all share an underlying commonality, which is basically appearance, in many cases, appearance of unconventional superconductivity near a point where magnetic order is melted at low temperatures, non-Fermi liquid metallicity in the normal state, and the fact that unconventional competing instabilities always seem to occur precisely around this range where the normal state is non-Fermi liquid. So what I want to focus on is also the data which was first done by Ian Fisher and company for this material, and Sitikanta Das and Suchitra Sebastian have redone this for the strontium compound, in which case the tetragonal orthorhombic distortion and the antiferromagnetic transition occur simultaneously, in contrast to what happens in barium 1 to 2. However, the resistivity data are very similar to what Fisher and company observe, and in particular what you see is that along the shorter direction, remember I told you that B is smaller than A in the orthorhombic structure. So what you see is nevertheless along the shorter direction, the resistivity is just basically the onsets shows an anisotropy which onsets about 40 Kelvin above the structural transition even for the parent compound. And if you look at the resistivity magnitude, it's indicative of a bad metallic state. Now this bad metallicity actually increases when you dope, in contrast to what you would expect naively. Further, the anisotropy also increases, and in particular the B-axis resistivity actually shows insulating-like behavior right up to lowest temperatures, and transition to superconductivity in the underdoped regime is actually seems to be from an insulator-like state rather than a metal as far as this direction is concerned. But on the other hand, along the A-axis, you still see very bad metallicity with quasi-linear temperature dependence. What is important to note is that this anisotropy vanishes exactly around or at optimal doping. So the question is, does this hide a kind of criticality associated with the spontaneous breaking of the discrete rotational symmetry of the square lattice? And what is its connection to superconductivity? How may this arise from a normal state, and so on? There is independent RPES data from the Fisher group, which basically shows that the band structure itself is anisotropically renormalized even above the structural transition. There is additional evidence for an electronic state, which one may dub as an easing nematic state. What about superconductivity? So, is it nodeless, or are there in-plane nodes or accidental out-of-plane nodes? This question becomes important. It's a multi-band system, and the Fermi surface in different systems shows variable degree of warping along this along Kz, similar to what one knows from the well-known strontium-Rutherford case. And in that context, there was evidence from heat conductivity measurements and so on that there were accidental out-of-plane nodes.
For the same system or for different systems?
Pardon? Okay, so here it depends on which system you're looking at, because different systems have a different degree of C-axis warping. So for example,
saying like for the same system, you see in-plane nodeless and out-of-plane penetration nodes?
yeah, so I'm coming to that. Okay. So if you take the 1111 sum of the 1111 superconductors, the penetration depth goes exponentially as you lower down the temperature to 0, which would be indicative of nodeless gap. But if you look at the 122, which I have shown you here, and these are for different families of iron arsenides, including 1111, 12, 2, and so on. All of them show a penetration depth which is linear in temperature, suggesting line nodes. Okay. All right. So, in addition, there is C-axis thermal conductivity data by the Taillefer group, which basically finds no in-plane nodes, but proximity-induced interband out-of-plane nodes along the C-axis. Because along the C-axis, thermal conductivity shows a power law decrease, quasi-linear power law decrease as you lower the temperature, but in-plane thermal conductivity shows an exponential drop. So there are no in-plane nodes, but out-of-plane nodes in the 1 to 2, at least. In iron selenides, on the other hand, there are no accidental nodes because the Fermi surface of the iron selenides has very little warping along Kz. So there is a direct correlation between the kind of Fermi surface you have and whether you have accidental gap function nodes or not. Right, so this is basically putting it more explicitly in a figurative sense. If your Fermi surface, the central pocket has a large degree of warping, then your gap function may intersect it along certain Kz points along the Kz direction, resulting in accidental nodes. But if there is very little warping, you will have no nodes whatsoever. So the idea in the early days of iron arsenide superconductivity was basically that the in-plane gap function has a what is called extended S plus minus symmetry. And what we proposed is that depending on the degree of warping of the C-axis Fermi surface, this component which is out of plane could also kick in and give rise to additional accidental nodes in the gap. But this is not all, because the high upper critical fields in iron arsenides also tell you that the superconducting coherence length is short. So one is not really close to a BCS regime, but rather closer to a BEC limit. Further, this form factor of the effective pairing interaction suggests that basically you have renormalized residual nearest and next nearest neighbor interactions, plus a proximity-induced pair amplitude on the z-square band, which might be relevant. Okay, so this is more of the same. Other similarities with the cuprate. So there is sizable spectral weight transfer across the superconducting transition. And as expected, this is a coherence restoring transition because the normal state is heavily incoherent with no well-defined Landau quasi-particles, but a gap opening gives rise to coherent features below Tc, exactly as what is seen in cuprates. In particular, there are sharpened low-energy kinks which are orbital dependent in angle-resolved photoemission. The resonance mode in INS, whose ratio to the gap function is basically exactly similar to what is found for cuprates and F-electron systems near optimal doping. Okay. So all these basically put you in a regime where the normal state is incoherent, suggesting sizable correlations, giving way to unconventional orders which either break the four-fold rotational symmetry of the square lattice or give rise to Cooper pairing. But the Cooper pairing itself is unconventional in the sense that you cannot anymore think of the instability as arising from well-defined Landau quasi-particles, since a lot of data shows that the metal is a bad metal and so should not have Landau quasi-particles. Okay, so for theory, what this puts a lot of constraints. suggests that this bad metallicity usually associated with proximity to Mott criticality and electronic nematicity may be related to an underlying avoided quantum critical scenario. So what is the source of this quantum criticality? Is one question. So what can give rise to bad metallicity, resistivity is quasi-linear in T, etc. So as mentioned, these are uncanny similarities to other well-known examples where Fermi liquid theory, one is forced to discard Fermi liquid views. So an important consequence of all this is basically that in a selective Mott critical picture, since a subset of the Fermi surfaces are basically eaten up from the unperturbed band structure, the resulting magnetic instabilities would basically need a reinterpretation, since one would not expect the nesting, which was seen in LDA calculations, to persist when the Fermi surface reconstruction occurs in the sense of selective Mott. Okay. Right. So on the other hand, one also knows from all these examples that basically if you overdope, you gradually go over to a more or less conventional looking metal, at least at very low temperatures. But the important thing to notice here is that whenever you recover conventional metallicity, you also destroy superconductivity. So there is a direct correlation between having a bad metal and unconventional high TC. Okay. So given all these, our strategy was basically to first attempt a reasonable description of the incoherent normal state itself, and this view has been taken by a lot of groups from the beginning of 2008 itself. There is an alternative view which basically posits that the antiferromagnetism in iron arsenides basically is dominantly driven by a Fermi surface nesting, as one would expect from the band structure calculations for these systems, and that when you dope, the antiferromagnetic instability is basically preempted in favor of superconductivity. Okay. So, I hope to have presented a limited bit of evidence. There are more evidences which would push you into a same straitjacket. Is basically that the normal state itself is such that you have good reason to question the existence of well-defined Fermi liquid quasi-particles. And if that is true, then the magnetic instability would need reinterpretation. Okay, so the first step was to basically ask this and see whether a reasonable description could be achieved. But then if so, the idea was to basically look for the germs of competing orders in the most relevant channels in the residual interaction, which basically should arise in such an incoherent metal, because it cannot continue down to 0 temperature. You would need to quench the large entropy of this strongly fluctuating state before you went to the T equal to 0 limit. And so relevant residual interactions must destabilize this incoherent metal. And so whether that could be achieved within a starting point which would be capable of describing normal state incoherence was the issue. Right. So basically, operationally, the starting point was to use DFT, the LMTO in our case, to compute the 5 bands, 5D bands in iron arsenides. And the idea behind neglecting the arsenic P states was that if you look at the LDA density of states, the weight of the arsenic P states is negligible or 0. Okay, so we restrict ourselves to 5 D bands of iron, and I'll get to that in a minute. This is the on-site orbital energy of the 5D states. This is the local Hubbard U, intra-orbital Hubbard U, inter-orbital Hubbard U, and the J Hund, which is basically approximately related to the rotational symmetry on a single ion. So furthermore, to simplify things, we work in a basis which basically diagonalizes the one particle density matrix in LD. So that simplifies things because one can work with matrix propagators which have elements which are the diagonal elements are the most dominant and off-diagonal elements are small. In the absence of that, this whole scheme just becomes terribly complicated.
Beyond those stages, how many electrons?
6. And you are adding electrons when you dope cobalt to iron, for example. But it is 6d electrons, and the xz, yz orbitals which are degenerate are partially filled. So there is an intrinsic propensity to basically break this orbital degeneracy, and I'll come to that. But what that suggests is basically that an orbital order may preempt magnetic order, and if there is a ferroorbital order, it would induce a structural transition by coupling to appropriate symmetry adapted phonon modes. And indeed, in all the iron arsenides, you see that the structural transition always precedes the magnetic transition. And right, so that point of view was first taken by Philip Phillips, among others. And that's what I'm going to basically look at with the DMFT formulation. So the solver we chose was a simple iterated perturbation theory solver. So for the one orbital case, at half filling, away from half filling, it yields excellent agreement with dynamical DMRG data, which was shown by Hallberg and Rosenberg around 2004. For the multi-orbital case, the agreement is not quite so good as for the one orbital case, though qualitatively the picture is very similar. So in view of the advantages which a diagrammatic solver like this presents, so one can calculate all response functions at arbitrary temperatures for arbitrary filling. There are no difficulties associated with analytically continuing Matsubara frequencies onto real axis and so on. So in that, taking that kind of constraint in view, we adopted the simplest solver like MOIPT, but there are other solvers like NCA and so on, which could also be used for multi-orbital situation like this, though we have not done that. There's an alternative which was taken over by the Cotillard group, which have also looked at the normal state with continuous time quantum Monte Carlo, which is a much more sophisticated solver than the one we use. But so we checked our data against them, and qualitatively conclusions are similar, though there are obviously quantitative differences. Okay, so this is basically the technology. So for multi-orbital systems, there are local multi-orbital correlations which are basically encoded in a local two-particle interorbital average, which can be self-consistently computed within the structure of the multi-orbital DMFT basically by writing down an equation of motion for the Green function, for the higher order Green function. And so this basically corrects earlier attempts which basically used an artificial decoupling to treat these multi-orbital correlations within multi-orbital DMFT. And in practice, one also has to avoid double counting of interactions which are already treated on the average by LDA, so that's there's a prescription for doing that, which is the one we used. Yeah. Okay, so I'm going to come to that in a minute, but okay, so the whole thing, philosophy is to marry structural realism with many body correlations for a realistic system, and ask the question as to under what conditions would you recover incoherent metallicity, which is basically what experiments tell you the normal state is. And that kind of approach is known very well to work for a host of strongly correlated materials. By now there are 4 or 5 reviews on the subject, and this is one. Okay, so but having an incoherent metal state without Landau quasi-particles immediately suggests that coherent one-electron mixing is going to be an irrelevant process, because if quasi-particles are very short-lived, the hopping from one side to another is not a coherent process. Okay, so in particular, any ideas of nesting of well-defined Fermi surface sheets would run into trouble because in the very absence of the quasi-particle description. So what's the option? So there is one option we know from one-dimensional physics, where from the case of coupled Luttinger liquids. So in coupled Luttinger liquids, what happens is if you take two one-dimensional chains, each one of them in a Luttinger liquid state, then coherent one electron hopping between these two chains cannot occur because the holon and the spinon have a very small probability of recombining into a coherent physical electron in the infrared. And so since this cannot occur, one electron hopping is prohibited. Right? So in that, so if one does an RJ calculation to two-loop level, what one finds there is basically that even in this regime, two-particle hopping gets more relevant. Okay? So pair hopping arising from residual interactions becomes more relevant in the one-particle hopping, which is basically killed off by the orthogonality catastrophe. Okay. So, and this picture has been used very widely for organics and motivated Anderson to basically put forth a series of papers where he argued that a similar process should give you superconductivity in cuprates. Okay. So for iron arsenides, basically working in in this 5-band situation, one can evaluate this residual two-body interaction. And the way we have done it is we have basically assumed that the major players are the XZ and YZ orbitals, basically motivated by the renormalized Fermi surface. And these are coupled intersite, interorbital, and spin fluctuations. I mean, the spin and orbital degrees of freedom are very strongly entangled in the incoherent metal, and the effective interaction reflects this. So once one has an effective interaction like this, there will also be a proximity like effect which will induce effective two-particle hopping processes on the remaining Fermi surface sheets. And that is basically what one would want to consider. Okay. But looking at this, you see that basically within the DMFT formalism, which is single site, these are intersite interactions. So scale has a higher power of 1/d, and can be decoupled in a Hartree-Fock approximation. So when one does that, one ends up getting two fields, one in the particle-hole channel and one in the competing particle-particle channel, one being associated with superconductivity and the other being associated with particle-hole instabilities. And so I'm going to argue that these are basically linked to the unconventional superconducting phase and the nematic phase, which I was talking about. Okay. So basically, as advertised, this is what we are doing, and one can compute a lot of responses in once one has the DMFT green function, because for a lot of for transport, the vertex corrections do not enter. They do enter dynamical spin susceptibility and MR, etc. But however, I want to show that in some sense they may be small. Okay, so that's the starting point. We start with the 5 LDA bands, and of course they are degenerate for the XZ-YZ in the XZ-YZ sector. But you see already a very strong orbital differentiation in the band structures, which is what you would, of course, naively, straightforwardly expect. You have metallic density of states for certain bands, but band insulator-like features in others. And this is interesting because it's known that correlations in a metallic band would basically shift spectral weight away from low energy to high energies. But in a band insulator, the correlations would do the reverse, that is transfer spectral weight into the region of the gap. So there are different effects competing, which you can already see at this level. And what you can do is basically do a DMFT putting in a value of U of 4 to 5 electron volt, which is what constrained GW calculations tell you.
What are the different panels?
Pardon?
What are the different panels?
Yeah, so this is XZ-Y orbital density of states. This is the Z squared. This is the X square minus Y square, and that's the XY. Okay. So 5D orbitals. So what we find is if we put a U of U less than 3, there is no way we can explain whatever spectral and transport features are being seen as a, okay. But one really requires a U between 4 and 5 electron volt. And that is consistent with Gabi-Kotliar group findings, which basically estimated the Hubbard U using screened LDA plus GW, which to date is the best way of estimating U and so on in correlated systems. And they placed it squarely close to 5 electron volt. Okay. Right, so when we started in 2008, we did not do an LDA plus GW kind of estimate of U. We basically took the view, let us basically look for a U which succeeds in getting a satisfactory description to a whole range of normal state data, and then adopt those values. Okay. So you can see that with a U of 4.5, you basically get a very fair description of the one particle spectrum. This is photoemission, that's X-ray absorption. And there's more or less, some might say, too good a fit. And one would naturally be skeptical because you say, okay, I mean, I know that I have problems in photoemission line shapes in transition metal oxides. I have problems like what kind of state, surface states or bulk, is it basically probing and so on and so forth. Also in X-ray absorption, core level shifts which can mess up your analysis. So, I mean, the fact that this seemingly presents a very good fit does not tell you too much, though it is encouraging.
But LDA density of state
Yeah.
is shifted by time.
No. Okay, so the dashed line here is the LDA density of states. Okay.
It just it looks like the shape is okay. So how is the Fermi surface? Does it change?
Okay, so the whole idea now is to take the LDA Fermi surface, to put the renormalized band structure, to compute the renormalized band structure, and to ask what the correlated Fermi surface will be. I mean, it has no reason to be the same as the LDA Fermi surface because, especially if orbital selectivity becomes an issue, because some of the LDA bands will get Mott gapped when you introduce correlations, and so will not be seen in the renormalized Fermi surface. Further, in the orbital selective Mott transition, as in FL star theory, which was proposed by Senthil, Sachdev, and Foyta, what happens is that the Fermi surface, the whole idea of the Fermi surface runs into a bit of a problem because the surface which encloses the total number of electrons is not the perturbative Fermi surface, but what is called a Luttinger surface, which is defined by the zeros of the Green function rather than the poles. Okay, so there is a topological reconstruction involved. Okay, but before I come to all that, what I basically want to show is that the same set of parameters, also gives you a very satisfactory fit of the optical data. So this is for small u, and you can see that it doesn't at all agree with the data, but if you take a u of 4 EV, it just, you reproduce essentially the spectral distribution, or the spectral weight. Okay. And that's the optical conductivity itself. So what you can see is basically the coherent looking component, but there are also strong incoherent contributions to the optical conductivity depending on which of the orbitals one is looking at. And so these contributions are all incoherent contributions. The only one which suggests some quasi-coherent contribution is this. And it turns out that if I go over from U to 4 to 4.5, the whole spectrum gets incoherent. Okay. This was for the 1111 superconductor. So I can go further and basically look at the static magnetic response using the DMFT Green's functions and an RPA, a renormalized RPA using the fully interacting G's but neglecting the vertex corrections. So again, you see that the experimental data, which are the green points, basically are well reproduced by the DMFT calculation for U is equal to 4. The question is, okay, so there are issues related to why you see this kind of susceptibility, uniform susceptibility temperature dependence in the iron arsenides. I mean, this is reminiscent of frustrated metallic systems. A similar behavior is found in doped sodium cobalt O2, which is also a superconductor in a range of dopings, and is also frustrated. It's a triangular lattice multi-orbital system. So it turns out that this actually has to do with the frustration which I was telling you in the beginning when I was just making an introduction. The structure of the hopping matrix in the iron arsenides is such that the diagonal hopping is of the same, almost the same as the nearest neighbor hopping, which gives rise to appreciable frustration that enters in the DMFT in a limited way via the band structures and the fact that the effective interaction J of Q, which is used in computing the full chi of Q comma omega in a renormalized RPA, basically has these kind of effects, albeit in a limited way. But it seems that this suffices, and apparently the vortex corrections are small, and one might wonder why. Okay, so as advertised, okay, so before I do that, so we have also computed the NMR 1 over T1T, and it's known that it has a weak temperature dependence at high temperatures, almost constant but not quite. However, there is an enhancement of the 1 over T1T in the normal state, reflecting a pileup of spectral weight, which then decreases and shows a power law behavior suggestive of nodes in the gap function at T below Tc, as well as absence of any Hebel-Schlichter P. So you can do this for the normal state, and this is what many groups have observed in NMR responses in the normal state, as well as in the superconducting state, but I will want to come to this in a moment. So the idea is then, having found reasonable description with the reasonable agreement with the normal state data, go forward and use the idea that superconductivity results from a generation of an anomalous field directly from residual interactions in the incoherent metal. Study the superconducting state, because the resulting normal state Hamiltonian plus the linearized pair hopping term can also be solved without problems in DMFT, since the interactions have been reduced to bilinears in fermion operators. Okay, so as was found by many people in the earlier days, so in the normal state, as you can see, there is a very low energy kink, which is damped out by a normal state incoherent metallicity. But when you go over into the superconducting state, you see that this normal state kink-like feature actually sharpens up, reflects the coherence restoring nature of the superconducting instability, and is orbital dependent. It's an orbital, what is termed orbital selective kink sharpening in iron arsenides. When you compute the NMR relaxation rate and you have to include the anomalous propagators here, what you see is basically a lack of Hebel-Schlichter P, most probably due to strong incoherent normal state scattering, and a power law dependence roughly T cube, very close to T cube at low temperatures, suggestive of a gap function without with line nodes. So since given the normal state Fermi surface, these cannot arise from the in-plane part of the gap function, this. So we checked that if you took basically just this, what you would get is no nodes in plane. But if you basically use the form which you multiplied a cosine kz factor with this, then basically the gap function would show you precisely this kind of nodes if the Fermi surface was warped. Okay. So we opine that this power law behavior, roughly T cube, is basically coming from out of plane line nodes, in the 1-2 system, which is the one we have considered here. Okay. Right, so what about competing order? So I want to argue that the same residual interaction which gave you S plus minus, extended S plus minus superconductivity with possible nodes in the gap function in the particle channel can also hold the clue to the competing order, right? In fact, it must be a competing order because it arises from the same residual interaction. So if you decouple this in the particle hole channel, what you basically see is that one contribution is basically the lowering of the A orbital relative to the B. And then there are excitonic, interband excitonic terms, which also arise in the particle hole mean field, decoupling of the residual interactions. But the fact that this is pushed lower by the residual interaction automatically favors a finite orbital order as a leading instability of the incoherent metal. And the situation is in a sense similar to other multiband cases like the strontium rutheniates or like the 327 here or yeah. So there basically the nematicity is also sought to be understood in terms related to the ones I have been using here, though there is no characterization in terms of them arising from an effective residual interaction in a bad metal. So however, once this occurs, once the orbital degeneracy is lifted by ferroorbital ordering, the resulting state also breaks the four-fold rotational symmetry of the tetragonal lattice, and because these orbitals have a fixed directionality. And by symmetry, this couples to an appropriate lattice mode or strain via a Jahn-Teller-like term, where the delta represents the orthorhombic order parameter. So this directly induces structural transition at TS and as a consequence of this ferroorbital order. And a main static effect is to basically displace the XZ, YZ bands. This is a simpler effect related to static renormalizations coming from terms like this. There is additional dynamic modification of the line shapes, but I'm not going to get into that. We are doing that at the present. So, but this is precisely what is required in Arpes' work of Fisher and company, where they see that the XZ orbitals, the XZ band is basically pushed below the Fermi energy even at temperatures way above Ts and Tn in the nominally tetragonal structure. So the electronic state spontaneously breaks the four-fold rotational symmetry of the tetragonal lattice structure, and that's the electronic nematic. Furthermore, it's since associated with ferroorbital order, it is an Ising-like order parameter. And in absence of strain, which acts as a field conjugate to this order parameter, you will wash out this criticality, which will then only be manifested in the structural transition. Okay. So thus, as Phillips was the first to point out in our picture, the Ising nematic is a consequence of ferroorbital order. Given that it may couple to phonons or to strain, the universality class is that of a liquid-gas transition, and one can have first-order transitions ending in a quantum critical endpoint. And it's an interesting issue as to whether this is what is happening in ion pnictides. Right? Right. So there is a nature physics paper by Nevidomsky and collaborators which makes a more thorough study of that aspect, in fact. The important point I want to get to is basically that both the superconductive as well as the ferroorbital or orbital nematic, as we call it now, arise from the same residual interaction and compete for the same electrons. So they must be competing orders. And that point of view is not completely new, though it is new in the ion arsenides context, was proposed by Metlitsky and Sachdev in the context of the cuprates. Okay. So what does the onset of nematicity do? So once the electronic state breaks the four-fold rotational symmetry of the lattice, if one recomputes the DMFT spectral function in the nematic in such a state, then what one finds is because the A orbitals have been shifted downwards by this nematic contribution or by this ferroorbital order contribution, the A occupancy gets effectively increased, and correlations get stronger in the A band, which basically drive the system across the Mott transition. Okay. The XZ, corresponding to the XZ orbitals. Okay, so you see a pole in the self-energy of the XZ orbitals at 0 frequency, which signals an onset of a Mott insulator in the XZ sector.
The occupancy of the XZ band is more also.
Pardon?
What is the occupancy of the XZ band?
Okay, so it's not 1 or something. I mean, it's close, but it's not 1.
Close to 1.
No. Yeah.
So in this correlated state,
Yeah.
how many orbitals are in the Mott type state? Just the XZ band only?
Yes.
And some are completely filled with the,
Pardon?
and there are some bands that are just completely filled that have been band insulated.
Okay, so in the LDA,
Yeah.
they are all partially filled.
But now you just take one of the 6 bands and make that Mott-like.
It becomes Mott-like. Okay? Because correlations get enhanced once the occupancy of the XZ orbital is increased, once ferroorbital order is set in.
And the other 5 will remain metallic.
Yeah, they remain metallic, but they remain very badly metallic, as you can see here. I mean, the self-energy does not show anything close to minus omega squared. In fact, it's quasi-linear. Okay, with a finite imaginary part at 0 frequency. So these are, of course, finite temperature, but it's a bad metal along the other, along the B direction, for example. While you would expect it to be Mott-like along.
What shows the symmetry between XZ orbital and YZ orbital? Started with
Yeah, the residual interaction. Because if you rewrite it, basically you can see that this is the XZ is basically lowered by a small amount relative to YZ. That immediately induces ferroorbital order. And since the orbitals have a directionality, that also induces a spontaneous breaking of the 4-fold rotational symmetry of the square lattice. Right? Okay. Yeah. Okay. I'm done almost. Okay, so you can use so basically from this observation, you can basically calculate, and this is what we've done more recently, but I'm not going to show that. Please feel welcome if you want more information. What one sees is that the resistivity along this direction is insulator-like, and along the B direction is metal-like, but bad metal-like. And this bad metallicity actually increases with doping. As exactly as seen in the resistivity data that I showed you. So, in fact, this kind of accord motivates us to suggest that an orbital nematic order arising from ferroorbital order, which in turn arises from the residual interactions in an incoherent metal, is the main competitor to superconductivity in the iron arsenides. And antiferromagnetism arises once the structural distortion arising as a consequence of a nematicity sets in. Okay. So the implications of this picture are basically that there can be hidden first order nature near the optimal doping, and in particular in the coexistence, in the region of coexistence between antiferromagnetism and superconductivity, which may be the reason for some of the experimental features that people are beginning to observe, right? Yeah, so this was our earlier attempt, but more recently what we have shown is basically the appearance of a pole in the XZ self-energy basically makes this A-axis resistivity actually essentially insulator-like in the normal state. And the B-axis resistivity is also basically in the bad metal regime. So you can basically extend this kind of picture to other iron arsenides. So there are KFe, 2Se2 systems which are vacancy, so-called vacancy-induced, bandwidth-reduced systems. And in this case, the U/W ratio is large enough to drive this system into a Mott insulator state. And we basically reproduce that as well. Okay, the similar kind of thing occurs in iron selenides, which are bad metals. Okay, though there the c-axis warping is so small that you cannot induce accidental nodes along kz, and so in that case you would basically say that the pairing symmetry would be extended S plus minus. Okay, so the nature of pairing symmetry, whether you have nodes or not, depends on the fully renormalized electronic structure, which is quirky in a multiband system, depends on the system. Okay, so what this tells, among other things, is basically that in view of selective Motness, which implies that the Luttinger surface, which encloses the total number of electrons, is associated with the zeros of the Green function rather than the poles as in Fermi liquid theory. The whole idea of Fermi surfaces and its nesting properties that is invoked in description of antiferromagnetism in itinerant pictures may need a reinterpretation. Okay. Right, so that's the message, and this is basically what happens in a simplified model. So what you see is basically in the Mott localized sector you see appearance of kinks and waterfalls, while in the metallic sector you see basically total loss of quasi-particles. So that, if this is true, then if the question is asked as to how does an antiferromagnetic metal arise from such an incoherent metal, it may involve the topological aspect, topologically reconstructed Fermi surface aspect that is associated with selective Mott physics. Okay, so I thank you for your attention.
Thank you, Mukul. Questions?
Mukul, just wanted to find out that if people try to determine the superconducting pairing symmetry by doing any tunneling experiments, like zero bias conductance or on these materials.
Yeah.
And what do they show? Any idea? I mean, do they support S plus minus phase or?
Broadly.
Broadly so.
Yeah. So, okay, so with regard to that, there's one thing I left untouched, so because there's relatively relative lack of data. But at least for the SR122 system which we looked at, I mean, basically what we find if we try to fit these in the intermediate temperature regime, this B-axis resistivity fits to an activated Mott behavior. But then very close to TC, actually this cannot fit the data. What actually fits the data is a Halperin-Nelson fit to the resistivity. And that is a form which is famously associated with large phase fluctuations above TC. An additional consequence of that is basically anomalous diamagnetism, most famously encountered in cuprates, and that has also, there is only one experimental paper which shows this in the iron arsenide context. But there is also additional work by Laura Green which basically says that as long as you are in the underdoped regime up to optimal doping, there is an excess Andreev current above TC, 40 Kelvin above TC, while when you cross the optimal doping, the excess current is gone. Okay. So that's the only thing one knows from tunneling. But as far as the symmetry is concerned, there is no data which questions the S plus minus.
Any further questions? Okay, so let's thank Mukul once more and break for lunch. Thank you.